Hello, my name is Lawrence, and my project involved creating 3D reconstructions of objects from photographs. This is an implementation of the method done by Hertzman and Seitz. Many methods already exist for reconstructing 3D representations of objects from photographs, each with their own advantages and disadvantages. For instance, we can take multiple photos of a subject from different light directions and use the assumption of n.l lighting to construct a normal map, and then use that to construct a 3D plot. This method is relatively lightweight, but also requires the target object to be Lambertian. Another method proposed casts a shadow over the object that moves from left to right. We can infer the 3D shape of the object based on the shape of the edge of the shadow. The benefit of this approach is that it can produce detailed reconstructions that are to scale. However, it also requires a lot of setup and calibration and does not work well on dark objects. We have two goals in this project. First, we show how we can reconstruct a target object made from the same material as a reference sphere. We then show how we can extend this to also work when the target object is made from arbitrary materials. To begin, for same material reconstruction, we begin by taking multiple images of the target object, in this case a bottle, next to the reference object, a sphere, made from the same material. For each pixel on the bottle, we want to find a spot on the sphere that has the same normal. The way we do this is by finding a pixel on a sphere that is shaded similarly in every lighting condition. For each pixel in a bottle, we create an observation vector that contains the intensities of that pixel over all input images. Similarly, we create observation vectors for each point on the reference sphere. For example, the pixels at the red dots represent the components of one sphere observation vector. Finally, we can use the nearest neighbors algorithm to compute which point on the sphere corresponds to each point on the bottle. This allows us to generate a normal map of the bottle, which we can integrate to get a depth map and then a 3D reconstruction. Next, we extend this method to work for objects that are made of arbitrary materials. We will make a 3D reconstruction of a ceramic owl. The owl is painted with many different colors. Moreover, it also has slightly specular BRDF with specular highlights, which is a property which would have posed trouble for many other reconstruction methods. Our setup this time is different too. Rather than having just one reference sphere made of the same material as the reference object, we have multiple reference spheres, and we also remove the condition that one of them has to be made of the same material. The general idea is that we assume the BRDF of the owl is a linear combination of the BRDFs of the reference spheres. For each pixel on the owl, we try each pixel on reference spheres and try to fit them together by finding a linear combination of coefficients that make the most sense. Then, the pixel with the best fit is used to determine the normal at that point on the owl. Again, we can use the normal map to get a depth map and use a depth map to build a 3D reconstruction. The method proposed by Hertzman and Seitz is a lightweight way to make 3D reconstructions of arbitrary objects. For most objects, the only things we need are a set of reference spheres, an orthographic camera, and some form of approximate directional lighting. This makes the method very versatile. We were able to achieve good reconstruction results in the case where the reference and target objects are made from the same material. Unfortunately, for the more general case, there was a larger amount of noise and we did not achieve the same level of accuracy as in the original paper.